This is the beauty of problem solving. You will understand how to connect pseudocode and combinatorics together in this problem right now. So let's discover that.
Hello, guys. Welcome to Cheenta School of Statistics and Data Science. We are a team of extremely passionate teachers, researchers, and statisticians from the top universities of India and USA. To book a trial class for your preparation courses of IITJM MS, ISIM Stat, and CMI MSc Data Science, check out the first link in the description below. If you're enjoying the video, show some love by liking the video and subscribing to the channel. We welcome you again to this passionate community of budding statisticians and data scientists. Let's enjoy the rest of the video. Stay tuned and stay blessed.
Let's get this problem started. So S is a set of which consists of 1, 2, 3, and 4. The total number of unordered pairs of disjoint subsets of S is equal to what? This is the question. So repeating once again, SA is equal to 1, 2, 3, and 4. The total number of unordered pairs of disjoint subsets of S is equal to what? That's the basic question. So how do you approach this problem? How do you count the total number of unordered pairs of disjoint subsets? Pairs, that means A comma B. Okay, it's unordered. So A, B. Okay, it's unordered. So A comma B and B comma A are the same. That's the unordered part. Pairs of disjoint subsets of S. That means A intersection B will be equal to phi. There is nothing in between A and B. Right? So how, and A and B are subsets of S. How do you solve this problem? S is equal to 1, 2, 3, and 4. Right? We need to find A and B such that this set A and B, set of all sets, such that rather the number of elements, this is such that A intersection B equal to phi and A and B are subsets of S. These are the kind of sets we want. We want to count the number of such subsets. So how do you approach this problem, guys? Any idea? You are given a general number n.
Yeah.
That's the question. Because that's where your insight will come. Let's say you want to teach a computer to do this. Of course, you can tell the computer, yeah, sure, that A and B are, you can just make a for loop. If you want to write the pseudocode, you can make the for loop for like I and like for all the subsets. So you can make a list of all the subsets first. So let's, if you want to write a pseudocode of this, so you can write a list, you know, in Python list or as an array. In every list there will be a set, call the sets. So in the first you can make phi, nothing. In the next you have 1, 2, 3, 4, and these goes till the end. 1, 2, 3, or then my all possible subsets. And you know that this has 2 to the power n number of subsets, right? All of you know this, the total of 2 to the power n number of subsets of a set of size n. All of you understand that there are 2 to the power n subsets of a set. So now we have this list, okay, in, let's say, in Python or wherever. This list where all of the sets are there, all of the sets are listed down. So you can make this by making having a for loop, okay, a for loop. If you're writing the pseudocode of this, and then you say that for the set A in this list, let's call this list sigma in this, and you again write for B in sigma, okay, right? So you're taking 2 pairs of this. Check if like how many elements are common in, if the elements common is like this is null set or not. That means essentially you're checking if A intersection B is phi. Okay. So you're taking one from this, one from that, and you're checking whether A intersection B is phi. So if A intersection B is phi, so you have to count this somehow. Okay. Then if this, then count plus 1. or count is equal to count plus 1. So your this is your counter, right? Count is equal to count plus 1. This is your counter that you're counting if it's that. All of you understood this? Yes or no? It's a pseudocode kind of thing. Okay. All of you understood how to write the pseudocode idea here? So this is how you should write a pseudocode. Okay. First count all of this. Then, but there's another specific way of counting this, the total number of subsets, right? So you have to take like, first do it for one element subset, first do it for 0 element subset, that is 5. First then we do it for the 1 element subset, then do it for the 2 element subset, right? Then do it for the 3 element subset, like that. You have to do it. Okay. But probably we'll get some inbuilt Python. You understand? So first you have to do 1 element subset, then you have to do 2 element subset, then you have to do 3 element subset. But is that a wise way of doing it? That's the question. The answer is no. This is not a wise way, because it's so hard, right? It's so hard to do it for all the it's a very complicated, right? Now this is the beauty of problem solving. You will understand how to connect pseudocode and combinatorics together in this problem right now. So let's discover that. So let's forget all of this. This is a very bad way of doing it. Let's first, before we go to any of the solution of this problem, let's just write the solution down. Write an elegant pseudocode. Write the solution for the number of subsets first. Okay. Let's say Google asked you this question in interview. Okay, how will you answer this? Let's forget about CMI. Okay, let's understand how will you find an elegant solution. That's the goal. Okay, that's the goal of Cheenta. That's how we want to help you. Let's understand how we can write the solution for this number of subsets in a very elegant way. Clearly, like if I ask you, like the basic question is that how do you teach a computer to count the number of subsets? Simple. Okay, how do you teach a computer to count the number of subsets? Let's say for 1 crore elements, 1 crore size of a data for set. Simple. That's the question. So anyone knows how to count the number of subsets of a set? We use something called a coding, right? We use a coding. How do we code? So we make there are n sets, so we make an n tuple. We make an n tuple for this n elements. For this n elements, we make an n tuple, right? And what we do a bijection, rather a connection. We say that if we take a binary number set out here, binary tuple, n tuple, and we make a connection between this, and we say that it's a set if, so this set corresponds to 1, there's 1 in here, it's not there, 1, 4, it's not there, and then so therefore this is a set. Okay, so what we do is that we do a binary connection. So we make a connection between the binary n tuple right, binary n tuple and the subsets 1, 4. This is how we count, and essentially the total number of subsets is nothing but the total number of ways you can arrange zeros and ones in this n places, n tuple, right? So therefore it's equivalent to saying the total number of subsets is equal to total number of n tuples with 0 and 1s. When all of them are 0, the set is 5. When all of them are 1, it's this entire set. Okay, and how many n tuples with 0s and 1s are there? It's simple, because n pluses are there, each can have 2 options, 0 or 1, 0 or 1. So it's 2 into 2 into 2 into, for each option, each place it's 2 times 2 options. Total number of options is 2 to the power n, therefore. So therefore total number of subsets is 2 to the power n. So now this is how we can train a computer, right? How we can train a computer? You can train a computer, right? Or you can ask a computer, right, that instead of saving these details, you just look into the 0s and 1s tuple, which is pretty easy to find out, right? Like pretty easy to formulate. It's like, how can you make the subsets of all these 0s and 1s? You just ask a computer to make all possible subsets first for this 0 and 1, and then select one of them, and then select the next 0s and 1s. So you can easily write a, so essentially you have now for each subset, understand this very carefully, for each subset you have now one such tuple. So let's say A and B has this tuple 0 1 0 0 1 0 like this, and B has this tuple like 1 1 0 1 1 0 0 1 0 dot, 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 like this. Like, now they are saying this is how the computer is saving it, because computer is very good at binary stuff, okay, rather numerical stuff. So computer has saved all the subsets in this format. Now you have to count among the subsets how many disjoints elements are there, right? Now it's very easy. How do you make sure the disjoint elements is 0? I mean, how do you make sure A is disjoint, A and B's are disjoint? It'll only happen. So let's take an example. Let's say A is equal to 1 2 3 and B is equal to, or 1 to 4, B is equal to 3 5 6. Okay, let's say it's a 6 element set. So A will be equal to 1 1 0 1 0 0 and B will be equal to 0 0 1 0 1 0. Essentially you can see wherever there is 1, there should be like both of them cannot have 1 at the same place. How do you mathematically formulate it? It's simple, right? Anyone? How do you mathematically formulate it? By a single operation. So you want that wherever, so both can have 0, this can be there, but this cannot be there. So it's like the AND operation, right? If you're an engineer, if you're an electrical engineer or computer science, you know the AND get kind of thing, right? So what do you want? You want the outcome of this to be, this can be okay, this is sure, this is sure, this is sure, but this is not okay. So that means, what is the AND get? The AND get is nothing but the multiplication get. So you take the Hadamard product of the A and B. Hadamard product is nothing but element wise multiplication. So if you take the element wise multiplication, you get 0 0 0 0 0 and 0. Good. But let's say it was 1 here, then it would have been 1 here. So what do? You take the element wise multiplication, and since it will be either 0 and 1, take the sum of it. Right? Take the sum of it. So you can now you can do it here in a simple way. So if the sum of A dot B is 0, then A and B are disjoint. Otherwise not. All of you understood this, yes or no? So what you have here is the following. This is nothing but the all possible tuples saved in the computer as a list. Tuple 1, tuple 2, tuple 3, or tuple 2 to the power n. Right? This is how you are saved. Now you make a for loop for I in, or let's say for A in this, and for B in this. What do? You check if sum of A dot B is equal to 0, is equal to 0. If it's 0, that means count is equal to count plus 1. You're counting it. Initially you save count is equal to 0 because there is no count. If you want to understand the computational complexity, how much is the complexity? Let's assume that, here is complexity 1 n times, here it's 2 to the power n, 2 to the power n times, both of them. You're running, no, here we are not doing any computation. Yeah, because you have to, no, we are not doing any computation here, but here, sum. So you have 2 to the power n elements, you are kind of computing 2 to the power n times 2 to the power n. So you're multiplying it 2 to the power n elements, so 2 to the power n there, and then you're summing it up as 1, and then you're checking it 0, that's 2, so it's 2 to the power n plus 2 kind of thing. Okay, oh no, you're doing this now 2 to the power n times 2 to the power n, because there are two for loops, so it's 8 to the power n times plus 4 to the, so yeah, it's orders of 8 to the power n. All of you understood this? All of you understood this kind of computation? How many times you're comparing? This is important because this is not in the syllabus, but what I'm making you understand is that you understand that whether it's important for you to, like, how much time it will take. It's kind of an exponential one. It is not easy task. Exponential computation is like, if you have 1 crore, the computer will crash. So it's not easy way to check it.